population, you're limiting it to just looking at that second population. So we can come back up to this in a second. Let's just kind of look at some of these. So this vertical line means given. So when I ask you to read something, say given. So we're given a Venn diagram, albeit it's a 3-circled Venn diagram. So there's just overlaps, like we have people who own only cats. There's 10. These 6 own just a cat and a dog. These 2 own a cat, dog, and a bird. Yes, all 3 circles are overlapping there. And this 10 up here is just the overlap between birds and cats. So those 10 people own just a bird and a cat. So how many cat owners are there total? 28, yeah. 10, 10, 6, and 2. Yep. The cat circle is filled with 28. Now again, some of those are just cats. Some of those are cats and birds. Some of those are cats and dogs. Some of those are all 3. But 28 people own cats. Okie doke? So when we jump into this probability, this is the probability of owning a cat given that you own a bird. So immediately we limit our population. You have to own a bird to be considered. So how many of those bird owners are there? How many, Chris? 15. There's your bird circle. We're only looking at the bird circle if we use given probability. Given bird. So there's 15 bird owners. Out of those 15, and only out of those 15, how many of those own cats? 12. You see it? Okay, you've got the just a cat in addition, or people who will own a cat and a dog in addition. So there are 12 out of 15 there. Does that make sense? Okay, try B on your own. Probability of owning a bird given that you own a cat. Don't simplify for now, just to make us all on the same page. Vince, what'd you get? 12 over 28. Did anybody get anything different? So I'll check this. I tend to like to, I will always do the denominator first. I think about how am I limiting my population given that you have to own a cat. So I'm only looking at the cat circle, which is 28. Out of those 28, how many also own a bird? These 12. Perfect. Good. Keep going through C, D, E, and F, and then we'll touch base. Owen, what'd you get for part C? Natalie, what'd you get for part D? Also 4 over 19? Tess, what'd you get for part E? Oh boy, we got a lot of 19s going on. Makes me nervous. F. Chloe, what'd you get for F? Okay. I don't know if these are right. I know A and B are right. Raise your hand if you think one of those is wrong, and how did you do it differently? Bella? 4/15 for C. Anybody get anything other than those two options for C? Okay, so let me think through C. Probability of owning a dog given that you own a bird. So look up here for a second. Whatever your second thing is, that's what goes in the denominator. So given B, your denominator is your number in B. And then your numerator is always however many are in both. If you flip the order, it does make a difference. B given A is different because A is now your denominator and the number in both is still your numerator. So if you're using kind of that thought, given B means your bird circle is your denominator. And in your bird circle, 10, 12, 14, it should be out of 15 is correct. And then how many people own both the dogs and the birds? So that would be the overlap between here and here. And there are 4 of those. So 4/15 is correct. Anybody have a different answer than the other 3 that are up there for parts D, E, or F? So we all agree with D, E, and F. Quick check. Out of the dogs, dog circle is 6, 8, 10, 19. How many of those people also own a bird? 4. Perfect. Out of the dogs, which is 19. So it makes sense that given D, they both have the same denominator of 19 dogs. And then how many of those dog owners also own a cat? 8. And then given cats, your cat denominator was 28 before, so that's not going to change. But how many own a dog and a cat? So both would be 8. Perfect. Good? That makes sense. Okay. So the next one is a survey that was given, and the results are shown. The survey, if you just look at the chart, clearly was to check the box as to what color hair you have, and to check the box as to what color eyes you have. And we're sort of going to be looking at maybe potentially correlations between those two features, kind of like the blonde hair, blue eyes we just saw. This one's not giving raw numbers. It's giving the probability of having black hair with blue eyes. 15% of the people had black hair with blue eyes. 25% of the people had black hair with brown eyes, and so on. So it doesn't matter if it's a raw number or a probability. We're going to do it the same way. So if you look at this probability, and this is doing the same thing that we were doing just above, it's just we need to be able to do it with Venn diagrams, which it looks like you're already pretty okay with. You also need to be able to do the same thing and understand where to pull the numbers from a chart, okay? So looking for the probability of having brown eyes, given that you have blonde hair, means we should only be looking at our blonde hair population. So I would immediately, and I'm not going to do it too dark because I have other follow-up questions, but I'm limiting my population to blondes. I'm only looking at blondes. So what is this out of? 0.35, very good. And then of those blondes, so I'm only looking at that category. I'm not looking anywhere else on the chart. Of those blondes, how many have brown hair? Or brown eyes? 0.10. Yes? In other words, just blonde is 0.35, and then both is 0.10. That's why I like this way of phrasing it, because the numerator is always the both. And then whatever that is, 10 out of 35, that's your probability. 10 out of 35, that's the same as 10 out of 0.35. That equals 0.29 if I'm rounding to the nearest 100. So again, we're not quite there yet. We'll get there tomorrow, but I really want to highlight what we're going to use this number to do. What is the probability of having brown hair regardless of anything else? Or brown eyes, rather. Brown eyes, brown, 0.35, yes? So overall speaking, Your probability of having brown eyes is 35%. If you have blonde hair, though, we just found that your probability of having brown eyes did what? Did it go up or down? Down. I don't know how significant that 6% is. It could be coincidental. But the fact of the matter is, something about having blonde hair made your probability of having brown eyes go down. Does that make sense? So we are led to believe that there's some sort of effect there, some sort of correlation. Because if these two features had nothing to do with each other, then the probability would stay the same, right? Like if I compared the probability of having on, you know, a black shirt, you don't need to write this down, and I compared it to the probability of having on a black shirt given that your average is over a 90, I'm pretty sure those are going to be exactly the same, right? Nothing about getting over a 90 is going to change your chances of wearing a black shirt on this beautiful Wednesday morning, correct? So we'll look at like when that given probability affects it and when it doesn't. And if it doesn't affect it, they're independent events from each other. They probably have nothing to do with each other. And if it is affected, then they're not independent, meaning there's probably something there that's indicative of a correlation between hair color and eye color. Are we good with that? Okay. Try this one. Probability of red hair given green eyes on your own. Sierra with a C, what fraction did you set up? Oh boy, if you think I can hear you, you think I have the best teacher ears in the world. Say that again. 0.20 over 0.25. Did anybody get anything different? Jason? Anybody get anything different? Owen? Anybody get anything different? Okay. So we are restricting our population that we're looking at to just the green-eyed people. What is your probability of having red hair? We're looking at the probability of having red hair, but we're limiting our population to just the green-eyed people. So if I go to eye color and I go to just green-eyed people, I'm looking at that column only. So it should be out of 0.25. So that knocks off that one. It's definitely out of 0.25. Now, of those green-eyed people, which of those numbers is the red hair? 0.15. So that is the correct one. 0.15, in other words, is the both green eyes and red hair. 15 out of 25 is 0.60. So interesting. Another way of phrasing this is if you have green eyes, if you had green eyes, you had a 60% chance of having red hair as well. Anybody have green eyes in here? Is there any strawberry blonde runs in your family? Any red hair? None? That's an Irish trait, but are you Irish? Owen? No. You sure your eyes are green? I'll double check that. So what would we compare this to? If we just calculated the probability of red hair, but it was with a given conditional, you would compare this to the probability of having red hair, period. And what is your probability of having red hair overall? 0.20 out of 1, which is just 0.20. So having red hair is rare, right? 20% of people. Very rare. If you have green eyes, though, that's a huge jump. Now your probability of having red hair has jumped significantly. Does that make sense? That big of a jump is indicative of a very strong correlation. It's kind of unlikely that that would be coincidental based on the population surveyed. This might be coincidental. You know how it dropped. It didn't drop by a ton. That jumped by a ton. Does that make sense? Okay. What do we got? 901. Yeah, we will. So I've kind of already talked about this, and just in symbols, this is what I'm saying. You compare your probability of B with the same probability of B, but with a given conditional. If they are equal to each other, meaning they didn't change at all, kind of like this one, probably wouldn't change at all, they're considered independent events, meaning the color of your shirt and your average probably have nothing to do with each other. That's why those probabilities don't change. And you also can do it in the other order. Do you notice how on this given probability B comes first? Yes? And so you compare it with B alone. On this one, A comes first, so you compare it with A alone. It can happen in either order, but whatever you calculate alone, that has to come first in the given probability. Yes? So what I've been doing here all along, because I'm not going to get to it on the back, but this is where we're going, we don't have to worry about that one, is kind of assessing whether or not they're independent. If there's a change at all, not independent. Okay? There is some sort of correlation, no matter how big or how small, right? If there's a change. This one, it seems to be that there's even a bigger change. So these are not, certainly not independent of each other. There's something about red hair and green eyes that works together. Yes? Genetics. All right. Jason's going to pass around the stack of homework. Just take one and pass it down the line and let it snake through. And I'm going to pass out your sequences and series tests. While I do that, I have 2 minutes